Okay, so chapter 9 is all about sequences, okay? And sequences are different kinds of patterns that we notice. So your tennis balls, okay, he noticed that it was multiples of 2 or adding 2 each time. So if you did your figure number, right, the 1, 2, 3, 4, 5, or 6, and multiplied by 2, you got how many tennis balls there were, right? From each figure to the next figure, 2 tennis balls were added as we moved on, right? There was 2 here, there were 4, then 6, then 8, and then 10, right? Your water bottles, it wasn't adding something, it wasn't even multiplying by something, okay? But you saw perfect squares. Again, using your figure number, 1 squared, 2 squared, 3 squared, 4 squared. And then to get our last piece, 5 squared, I would have 25 water bottles, okay? Helmets, there were a couple of things happening. So it wasn't just one thing, okay? There were lots of different ways we could look at it. So looking at just the physical picture, you were adding 2 helmets to the bottom row, or to all the rows, and adding a whole other row to my figure each time, okay? Brennan saw the math kind of into it. He added 7, and then after that, after you add 7, you also added 4, and then an additional 4 each time, okay? Did Abidon's equation work?
No.
Were you all figuring it out? No? Close? Did Evan's work? Evan, what kind of equation did you come up with? N times what? 2n plus 1. Okay. So creating an actual equation is creating an actual rule, which we will also be doing that throughout this chapter. Okay. So today is just an introduction of all the different kinds we're going to work with and how we're going to display them. And then Wednesday we'll focus on just arithmetic. Friday we'll focus on just geometric. Okay. And then we are going to quest again next Wednesday, because this whole week is just chapter and we're done. All right. So just a couple of details about sequences in general. Okay. A sequence is an ordered list of numbers. Each number in a sequence is called a term. Okay, so those figure numbers, those were term numbers. The first term, second term, third term. Okay, each term A sub n has a specific position, which is n, in the sequence. So my A sub n was 6, but the n was 3, because it was figure 3 that gave us 6 tennis balls. Does that make sense? Kind of. Okay. So, like in this example, like right here, your n is 3. And then A sub n would be the 6 tennis balls that were in figure 3. We're in my third term. Okay? So you're going to use your term to find out your outcome. Okay? The relative positions of the terms make up the domain of a sequence, and the terms make up the range of the sequence. Okay? In the example shown, the 5, 10, 15, 20, 25, okay, that can be described with an equation or a rule of 5n. So my first number was 5. 1 times 5 is 5. My second number was 10. 2 times 5 is 10. My third number was 15. 5 times 3 is 15. Okay? That's how we're going to create the rule. We could use A sub n, or if we do like real life stuff, F sub n, or F of n comes in to show it's a function. Okay? The domain of a sequence may begin with 0 instead of 1, unless otherwise indicated. Assume the domain of a sequence always begins with the number 1. It could begin with A sub 0. A lot of real world things will start with A sub 0 to showing the starting of something, and then A sub 1 shows like after the first change occurred. So that's when your A sub 0 would come in, right? So let's just do practice of just finding the pattern, calculating the pattern, and writing our first 6 terms. So our first sequence is A sub n equals 2n plus 5. So if I have A sub 1, that means my n is 1. And 2 times 1 plus 5 gives us, there you go, 7. If I have A sub 2, that means my n is now 2. A sub 3, my n is now 3. A sub 4 means my n is 4. And the pattern repeats itself all the way through. So when my n is 2, what's my outcome? 9. How about when n is 3? 11. When n is 4? 13. When n is 5? 15. And when n is 6? 17. So my first 6 terms are going to be 7, 9, 11, 13, 15, and 17. Good. I want you to do this for part B. We have f of n equals parentheses, -3 parentheses raised to the n minus 1 power. All right, so find your first 6 terms of our next one. All right, when you're ready to check, look up here. Does it make sense that these numbers are switching back and forth between positive and negative?
Yeah,
Yeah, how come?
because if it's like an odd, if it's raised to an odd power, it like keeps its
If what's raised to an odd power?
the number negative.
A negative, yeah. So like if our base is a negative, so whenever it gets an odd exponent, it will stay negative. Okay. Good. All right. Let's compare here. Do you notice anything different possibly between these two sequences, the red and the blue, when it comes to like the pattern themselves? Thomas, what you think? Yes. How about the actual patterns? Dylan, what do you think? Which one changes linear? The one on the left? How do you know that?
Because if you were to graph it, it have like a slope of like just 2.
Okay, so Zach, without graphing it, what did you notice?
Just adds 2 each time.
Yeah, we're adding 2 each time, which is a constant rate of change, which ties into slope and into the lines. Good. So how would you kind of label that red one? If blue is linear, how do you think we're going to label the red? Possibly.
Quadratic.
Almost. But quadratics are powers of 2 every time. Right?
No.
Cubic would always be a power of 3.
Oh.
Exponential.
Exponential. There you go. So exponentials is when like your base stays the same, but your exponent changes each time. Right? You get yourself a little curve going on. Okay? So remember that, because that's going to be how we tell the difference between our arithmetic and our geometric sequences later this week. Okay? One of those is one, one's the other. I'm not going to tell you which one. You can probably figure it out. But just remember. What we're also going to do with our sequences is we are going to graph them. Okay? Which is a whole lot easier than you think it is. To graph a sequence, let a term's position number n in the sequence be the x value. And then the term a sub n is the corresponding y value. We're going to plot the ordered pairs by n and a sub n. So if my sequence is 1/2, 2, 9/2, and 8, the actual numbers in my sequence, that's your a sub 1, a sub 2, a sub 3, right? That's your outcome. Okay? What position is 1/2 in?
1.
It's the first term. So my first term is 1/2. Our second term is 2. Our third term is 9/2, or you can say 4.5 if you would like. And my fourth term is 8. So that is your new coordinates. Okay, so 1.5, 2, 2, 3, 4.5, and 4 and 8. So Dylan was talking about graphing it earlier. We're going to use that also later this week to help determine which sequence we're working with. Because we can plot them and actually physically see, is there a constant rate of change? Is there a curve going on? What's up?
So when you're like graphing it, when you're like connecting the dots, right? Will it ever pass the x-axis?
You were actually never going to connect the dots. So I'm glad you asked me that. Yeah, we're just going to plot our points. No, good question. We're going to plot the points and leave them alone. These are discrete functions, okay? Because I'm representing just what's in my list of numbers, so there's no in between. Thank you for asking that. Yeah. So you're only representing what's in the list, so it's only going to be discrete points. Good. I'm glad you asked that. There was a lot of erasing after you asked that question. So, no, that's good. No, I agree. Good job. All right, so now let's go into writing rules, okay? So when the terms of a sequence have a recognizable pattern, you may be able to write a rule for the nth term of the sequence. So I can find any piece of my sequence. I can find the 100th term as long as I know what the pattern is without having to do the first 99, okay? Describe the pattern, write the next term, and write a rule for the nth term of each sequence. So we'll do this first one together, and then you'll do the next one, okay? So my sequence right now is -1, -8, -27, and -64. Who has an idea of a pattern or what could possibly be the next term in this sequence?
Oh, it's like times.
Okay. That's okay. No, your brain's working though.
Oh, help. It's like, it's, okay. It's -1 cubed, -2 cubed, -3 cubed, -4 cubed,
Okay. So what's our next number going to be?
-5 cubed,
Which is
-125.
-125. Okay, so he noticed. He did. He noticed that each one is a cube, right? 1, 8, 27, 64, but they're also negatives. Okay? So the pattern we're noticing is negative perfect cubes. Okay? So the next term is going to be a -125. Okay? So he recognized, okay, well, -1 cubed, -2 cubed, -3 cubed, -4 cubed, and then to get our next piece, he took -5 and cubed it. So how could I write a rule for that using n? Like, how could I find the 12th piece? So it would be -n. Make sure you keep it in parentheses, which is what Rowan was saying. Keep it in parentheses, -n, and then to the power of 3. What's up?
It does though.
But cubing it keeps it negative anyway, so it doesn't have to be in
So, like -2 cubed is what you're saying? Would be okay to not put it in parentheses? Yeah. Yeah, with odd exponents, it does not matter. It's just good practice to keep it in parentheses because what if it wasn't? Right? So, yes, for this one, parentheses would not change our outcome. If that was a power of 2 or 4 or 6, it absolutely would. So if I wanted the 12th number in this sequence, you would do -12 raised to the power of 3. Yeah? We good? Kind of? All right, so the next one's a thinker. So I want you to think with a friend or someone close by. Okay? Our next one, we have the value 0, 2, 6, and 12. So talk it out. See if you can notice a pattern going on. What's the next piece going to be? And then what rule can I write for them? Okay, so this is what I'm seeing on a lot of people's papers. Okay? Like, you know the next piece is 20, then you're kind of stuck of like, okay, but what's the rule? Okay? So how did you get to 20?
Added 8
You added 8? Why?
because we got, alright, here's why. Because we got
+2 and then +4 and +6.
But that's not the same thing each time. So how would you write that using n?
I don't know.
Maddie, what do you see? So it is a pattern to recognize, right? That is happening. But to write that using n would be difficult. Maddie, what do you think? You add 2n?
You add to the
Something. That could be something. But so is it? It can't be n plus 2n, right? Because that wouldn't work with my first one. Bless you. But we're thinking the right way. These are hard sometimes. Dion, what do you think?
So like, you do 1 times 0, right? Then you do 2 times 1, then you do 3 times 2, so the multiplying number increases by 1 every time.
Okay, so he's saying,
You do 1 times 0, then you do 2 times 1, and then 3 times 2, and then 4 times 3, and then 5 times 4.
okay, yes. So you're, oh, okay, yes, yes. So my rule, you're multiplying it by the number before, right? So I'm multiplying 1 by 0. That was the number before it. Multiplying 2 times 1. There's another rule. Bruno, what do you think? Was that what you said? Yes?
It's also n squared minus.
Wait, what?
Yes. Or
12 times 11?
these are your ends. Remember, n is the term. In my first term, yeah. So something else that people might have noticed. 1 squared minus 1, or 2 squared minus 2, 3 squared minus 3. This one's not as obvious, but it also does work. 1 squared minus 1 would give us 0. 4 minus 2 is 2. 9 minus 3 is 6. 16 minus 4 is 12. 25 minus 5 is 25. So that's another way to write the rule. Which, if you look at it, isn't that just n times n minus 1?
Yeah.
Doesn't that equal n squared minus n? Right? What is it? No cap? Is that, I don't know what those words mean.
No cap.
No cap? Okay.
But
That means truth, right? So they would both be recognized. So like when we did our helmets at the beginning, we had different rules and they all kind of worked. Okay? Because they were all technically the same thing together. Okay? So there's 2 different ways to recognize our rules here. Okay? When you write the rule, though, it has to work for every single piece. And your n is which term you're referring to. Because you need to use it to find another piece. If I want the 20th term, I gotta be able to plug in 20 to the rule we're making to find that piece. Alright? Alright, last thing. We're building pyramids with apples. Okay? You work in a grocery store, and you are stacking apples in the shape of a square pyramid with 7 layers. Write a rule for the number of apples in each layer, then graph the sequence. Okay? So we have a little picture that's pointing to me to my first layer. So in my first layer, how many apples are there?
1.
There's 1 apple. I'm definitely going to do red. We're talking about apples. There we go. So how many apples do you think will be in layer 2?
4.
How many apples will be in layer 3?
16. I'm just kidding.
Okay? What pattern are you doing? You're squaring them. Why? What told you to do that?
Because that's the volume of a pyramid per layer. That's how you calculate it.
It's a square pyramid, so each layer is a square. Okay? So keep that pattern going. Fill in your table and plot your points. All right, so our table and graph should look like this. So our rule, because it says to write a rule, so any layer would be the layer squared, right? This is the rule for how we created our table. We kept squaring it. Okay? What if your manager is like, cool, but like I'd love a couple more layers? So what if he told you to remake this but using 9 layers instead of 7? Okay? How many more apples would you need to make 9 layers? Ready, set, go for it. Talk to me. So we already have layers 1 through 7. If I want 9 layers, I need to add apples to make layer 8, and we need to add apples to make layer 9. How many apples would create layer 8 for you?
64.
You would need 64 apples to make layer 8, and how many apples would you need to make layer 9?
184. I mean 145.
So to create layer 8 and layer 9 together, you would need 145
I was 10 off.
additional apples.
Yeah, I got one.
I have a bonus question for you. Hold on. So adding 2 more layers, you need 145 apples to do it. Okay? Bonus question. How many apples in total do you need to make the entire pyramid with 9 layers? How many apples total would you need to create this apple pyramid, square pyramid with 9 layers? Almost. How do we get 285? Yeah, you add up all your perfect squares between 1 and 81. That is technically a series. So a sequence is like finding the pattern, and then a series is adding them all up.
Have you ever played sequence?
No. All right, good job.